10,000 some odd years, we've only had diamond and graphite.
Now at the end of the 20th century, we've discovered a third form of carbon.
Chemistry has, by and large, been the subject of studying carbon. How could we have missed something like this?
This story of discovery and revolution in chemistry begins with astronomy, the death of stars and the birth of planets. Dying stars are pumping out carbon atoms into the interstellar medium. Diamond and graphite are the earthly forms of pure carbon. Its atoms can exist only as molecules. In living tissue, they mix with hydrogen, nitrogen, or oxygen to form organic molecules that build creatures and trees and decay to soil, coal, and oil. But in space, atoms can exist alone or in chains and clusters.
We were working on some longish chain carbon molecules, and I wanted to do experiments in the laboratory to see whether we could simulate carbon star atmospheres and the chemistry in these objects to see whether we could in fact see these long chain molecules in the laboratory.
The story also begins with light. All molecules absorb light energy as it strikes them. Each molecule's absorption is unique and shows as a pattern of dark bands in the spectrum. A fingerprint. Be it in radio, microwave, visible light or infrared, on Earth or in space, somewhere in the spectrum, everything has a signature. So the contents of interstellar dust can be deduced from their absorption bands. And there is one signature that has been seen but never identified: the diffuse interstellar bands.
The thing that got me most interested about astronomy was this amazing mystery of the diffuse interstellar bands. None of these have yet been explained by anything on Earth. And so when I was a young assistant professor at the University of Arizona and I began talking with the astronomers, I began to realize that perhaps there's something out there that we hadn't made on Earth, and perhaps the discovery of that would be a really exciting challenge to pursue.
In 1982, Huffman took a sabbatical in the Black Forest of Germany at the physics lab of Wolfgang Kretschmer in Heidelberg. They wanted to study the ultraviolet spectrum of tiny particles of carbon dust.
This is, so to speak, historic machinery where Don Huffman and I made the first dust experiments.
It worked like an arc welder, pushing an electric current through a couple of sticks of graphite, carbon, but inside a bell jar in a vacuum. It made a cloud of vaporized graphite, carbon dust. They collected the dust, and shining an ultraviolet light through it produced a UV absorption spectrum. And it was not at all what they expected. Instead of a smooth curve, at a wavelength of about 220 nanometers, they got a line with a double hump, a sort of double absorption band.
Kretschmer dubbed this camel spectrum, and they were there after we called it the camel spectrum. And that set off a discussion, a long-time discussion between Kretschmer and I. I've suggested originally that maybe we had a new solid form of carbon.
He was believing that it must be something very, very peculiar, and I was believing it is just junk.
3 years later, Harry Kroto would have given a Nobel Prize to get his hands on that junk. In 1984, Kroto visited his friend Bob Curl at Rice University. There was the best system in the world for looking at clusters of vaporized atoms, in the hope of creating new materials to make catalysts or semiconductors.
Most materials like the silicon, for example, need to go to many thousands of degrees to be vaporized. Well, there's an easy way of doing that with these modern lasers. Here's a silicon disk, bring it on in, and as we come into the focus here, we're generating a little plume of silicon atoms, well over 10,000 degrees, easily hotter than the surface of any star. But what good is if it's just here in the air forming silicon oxide, actually? What we really want to do is to collect these silicon atoms as they're knocked off, aggregate them together in a little cluster into this big machine down here that we built to study those clusters on the fly. Ultimately, it comes on into this large chamber, and on the inside of this, it strikes at the back the target material that we're trying to vaporize to produce clusters.
The clusters rush back, get ionized by another laser, and pushed up by an electric field to a mass spectrometer. It counts how many clusters there are and how many atoms in each.
Overall, it's a very simple apparatus, although it looks rather forbidding.
Smalley was working on clusters of silicon, but when Harry saw the lab, he thought of carbon and space.
Hotter than the surface of any star.
When I went over to Rick's lab and saw the machine in the flesh, it was just fascinating. And almost immediately I realized that if we substituted graphite for silicon that was in at the time, we can make a plasma similar to that which one has in the shell of a carbon star. We could simulate that chemistry and perhaps make the carbon chains that we had detected a few years earlier in space.
What followed, none of them will forget. Harry worked with the students, doing run after run of graphite vaporized by laser. His friend Bob Curl bounced ideas between them. Smalley drifted in and out to see how they did. It was practical, creative science at its best. This is the mass spectrum of clusters they produced. There were small clusters with odd numbers of atoms, then a gap, then even-numbered clusters, all suggesting unusual chains of carbon. But the big ones, twice as abundant as the rest, were the clusters of 60 atoms, C60. Again and again, 60 was the cluster that carbon preferred. Now Rick really did get interested in what Harry was doing. Why did carbon atoms form such a stable cluster? What was special about the magic number 60?
If there's any element we know how it bonds, it's carbon. That's what chemistry has largely been about for several hundred years. And we know with many examples that carbon likes to bond, usually with 4 other atoms. And in fact, in diamond, the pretty form of carbon, that's exactly what it does. I have a model of a little piece of a diamond lattice here. You can see that each carbon atom, for example, this little black dot, connected through these green bonds to 4 other carbon atoms. That is, except if they're on the surface, in which case there aren't the little black balls to connect with, and these dangling bonds don't know what to do. Now, ordinary diamond doesn't have a problem with this because hydrogen is used to terminate each and every one of these bonds. And in fact, if you have a diamond ring on your finger and you move your finger across the surface of the diamond, you're not touching carbon at all. Because there's hydrogens on the surface. In fact, you're rubbing a single atomic layer of hydrogen on the surface. But we knew we didn't have any hydrogen in the machine. Well, there is another way the carbon can bond that we know about as chemists. That's with just 3 other atoms. And the most common form of this, as we know, is just plain old graphite, which is, in fact, infinite planes, or effectively infinite planes, huge planes of sort of chicken wire lattices like this, connected 6-membered rings, each carbon connected with 3 others. And in graphite, there's one plane against another stacked up. But once again, here are these edges.
These dangling bonds should make a tiny cluster attract other carbon atoms and grow. Yet here, they had a cluster that stopped at 60. Why?
We wondered what could possibly make it so strong. We thought about many possible structures, and as it went up and down like a yo-yo on various runs that we did, we came to the conclusion that perhaps it was a closed cage of some sort.
Let's suppose we go back just to a single large sheet. And this has roughly 60 carbon atoms. Obviously, it has a lot of dangling bonds around the edges, but suppose somehow we're able to wrap around so that these dangling bonds here could connect to those dangling bonds. Maybe there was some way of wrapping that sheet around to do it, but we couldn't really imagine how that would be done.
One image, which was in my mind from way back, it was that of Buckminster Fuller's dome at Expo 67.
The design of lightweight spherical structures was the life's work of the American architect Buckminster Fuller.
Add up to 3 360 degrees. Therefore, it becomes a plane and goes to infinity and won't return upon itself. From the common center, we begin to get then spherical triangles.
His was the idea of the geodesic dome.
There are now over 4,000 of his domes dotting the Earth's surface, made of every material from metal to cardboard. But for Fuller, the success of his domes is merely one proof of his theories. What interests him now is the fact that his ideas have stimulated the thinking of many scientists.
I'm an explorer in structures. I'm interested in the fundamental principles by which nature holds her shapes together. I'm going to take this away and we find that our cube has no structural integrity whatsoever. So because the structural exploration that I've been engaged in over a great many years has now become of interest to the scientists themselves.
In fact, the parallel between this and your dome is very close. I mean, it's fantastically close. They are based upon the same structure, although they are realized in different ways. You have struts and tripods. Yes, we have rubber tubes and chemical bonds.
Yes.
For many of the scientists who have met Fuller, the experience has been rewarding. He does not set out to copy nature, but he is pleased, though not surprised, that scientists are finding that nature's solutions to her own structural problems coincide with his.
I'd been in Montreal at Expo 67, and I remembered going into Buckminster Fuller's dome and pushing my son in a pram up amongst the escalators and towards the struts, the intricate structure that held the dome together. In fact, one aspect of it is that it really did seem to be made up almost completely of hexagons.
Here, after all, we had a hexagonal sheet. Maybe if we figured out how Buckminster Fuller did this, we could figure out how to curl these things around on each other.
The other thing that I remembered, as well as Buckminster Fuller's geodesic dome, was a star dome, a map of the sky on a polyhedron that I'd made for my sons many years beforehand. In my memory, it had hexagons, but it also had pentagons.
Rick went home, drew out and cut up little paper hexagons. Harry went to bed thinking of the star dome, stored in a box in his basement. 60 jelly beans joined by cocktail sticks was the scheme adopted by graduate student Jim Heath. The jelly beans collapsed. The hexagons would curve only by cheating. Hexagons side by side only make a flat surface. Then Rick remembered the pentagons that Harry had talked of. Hexagons round a pentagon. They automatically curved. They made a bowl shape. Then more curves, more and more, all linking. A geodesic sphere. 60 points, 60 carbon atoms. The shape of C60 formed in his hands. Their paper to Nature was a front cover story. They named their structure Buckminster Fullerene. Buckyballs.
We call that the icosahedron.
Perfect symmetry in a molecule.
It was so beautiful that it just had to be right. But there were people that needed convincing, quite a lot. And the question is, how could we set about proving that it had this structure?
In Houston, they tried to prove the structure by breaking the cluster apart and measuring the pieces.
We can make the laser tremendously powerful, enough to drill through a hunk of metal. We found that we could finally turn it up so that, yes, finally C60 would fragment. The amazing thing is that it fragmented by losing little C2 pieces, dimers of carbon. The result is just simply, you've got a ball, you blast it with lasers, get very hot, it evaporates C2 off the surface and it shrinks. And as you keep blasting laser energy, it shrinks more and more and more.
They got readings of C58, 56, 54, and on down till the strain on the atoms was too great.
It's just what you would expect if, in fact, it really were these closed cages. When you blast it, there aren't any edges, no places can just fall right off, so it shrinks down until finally, critically, at C32, the next step is it bursts. For most molecules, that would already have been considered a proof of the structure. But this is too important a molecule to just casually say you've proved it.
One thing that was clear was that all the pentagons were isolated and all the hexagons were linked. That seemed to be a critical factor in the stability. And I started to think at what stage that would occur again. I knew it couldn't happen for anything less than 60 atoms. And as I went on higher and higher, I realized that I couldn't do it again until we got to the number 70. We'd already got a structure for 70 in which we take the two halves apart and we put an extra 10 carbon atoms along the waist. And then I realized that this explained the second peak. Now, we had found that the C60 signal always had a companion, C70, and I used to call the two together the Lone Ranger and Tonto. At that point, when you have a hypothesis which explains two major results, then you can be sure it's right.
So Harry persuaded the British Research Councils that C60 research was worth funding. He bought a cluster beam. The goal was to make C60, to be the first to hold it in his hands.
So for years, actually, squandering the life of my major graduate student, Jim Heath, we scraped soots up, put them in test tubes, sloshed them around and looked, and for years all we saw was soot sort of floating around or sitting at the bottom. Well, it's a lot of fun to do for a while, but for a year and a half it gets to be kind of boring. So we pretty well gave up.
But soon, paper after paper appeared from theoreticians. They were having a field day, predicting the properties of such a molecule. The perfect symmetry of C60 made it possible to calculate how a buckyball would rotate and vibrate. The movements of the molecule and its electrons are what causes light to be absorbed by it. So absorption bands for C60 were calculated. Its fingerprint in the spectrum, at least in theory, was available in print. And in Tucson, Don Huffman had read it.
When I saw the Krotos-Moly paper in Nature, I was very excited because I immediately began to think that perhaps the camel sample wasn't junk after all.
So he set a graduate student with a bell jar to make soot that would reproduce the camel.
It's really a very simple experiment, which is a good thing because it was such a long shot. It's a simple device. There's a carbon arc discharge in a vacuum chamber with a little helium in there. There aren't very many things you can change. We changed the tip size, we changed the voltage and the current, but it turned out that the most important thing was the pressure setting. When you have the pressure at about 100 torr, which is about 1/7 of an atmosphere, those two funny bumps, the camel spectrum comes back, the thing that we had seen in Heidelberg.
In Heidelberg, Kretschmer put their sooty specimens into an infrared spectrometer. Kretschmer presented their results at an astronomy conference in Capri, and the paper found its way to Harry Kroto.
When I read it, it was such a simple way of making C60. I just couldn't believe it.
Believe it or not, he dispatched 2 students to evaporate carbon.
We've been collecting it several months. So one Friday, one brave Friday, I had, I suppose, perhaps half this full of soot, and I thought I'd better do something. And one idea was just simply using a solvent to try and dissolve C60 out. So I got half of the soot I produced, and I basically just got some benzene, put it in the tube, and shook it up with the soot. Just shook it up, put it on the top of the shelf, and left it there over the weekend. When I came in on Monday morning, there was this red solution. I went round the laboratory going, look, C60's in here. And everyone was sort of going, yeah, okay, John. but it worked out in the end that, in fact, that's exactly what it was.
The amazing thing is that the whole process was so incredibly simple. Once we found that the carbon-60 was soluble as a red liquid, all we had to do is dry it out, and that left us with the solid that we're so eagerly seeking. The easy way to do that is just to pour it on a hot plate and let it dry for a few minutes, and there's the solid that we wanted to do the experiments with. Now, the way it really happened was Kretschmer called me from Germany and said, if you just take a little vial of the red material and you put a drop of it on a microscope slide, then you will see an incredibly beautiful sight. So I reproduced the experiment by putting a tiny drop of the red liquid on a microscope slide. And in just a very few seconds, as a matter of fact, I was able to see these beautiful little crystals, which were hexagonal platelets of brownish orange color.
No longer fleeting atoms in a laser, not merely in red solution, now a new solid, pure carbon crystals.
We realized by this time that we were surely seeing a crystalline form of carbon-60, which was really a genuinely new form of carbon, and that we were probably the first people on Earth ever to even see this sight.
This is the first ever film of a new carbon, Buckyballs crystallizing before your eyes.
And as a solid-state physicist, it was incredibly nice to be able to say, aha, now we've got something that we can really begin to experiment with. We can see it and work with it. And that was really the moment of high excitement for me.
Now we have spherical molecules. We have benzene rings that are assembled in 3 dimensions on a sphere. And the chemistry and the rules of the chemistry of Buckminster fullerene are entirely different from those that we are known to use. So we have to invent new chemistry.
The aim is to attach other chemicals. Then more can be done with C60. Chains of buckyballs, polymers, molecular wires, all become possible. Buckyballs have also electrified solid-state physics. AT&T's Bell laboratories have grown crystals of C60 and put potassium atoms in the spaces of the crystal lattice. C60 loves to attract electrons, and potassium loves to give them away. They found the crystal was an electrical conductor. 3 weeks later, that it was a superconductor with no resistance to electricity. That means that everyone wants to work on C60.
The amounts produced so far are tiny. In fact, this is about 1/10 of the whole of the world's supply. But uses are already coming to light. Because of the way the balls pack together, it makes an amazingly absorbent material. The balls could also store electric charge for batteries or computer memory, or even act as a lubricant. With fluorine bonded to the Buckminster fullerene, it could become a super non-stick surface. The ball-like molecules rolling like these glass spheres to give an almost friction-free surface. It seems that Buckminster fullerene could affect all of us, and with researchers across the world now working feverishly on it, one day this powder might become as common as graphite, or diamond at least.